Okay, we're recording. Welcome everybody to our AI seminar. Today we have an internal speaker actually from USC. So Chaoyang is a PhD candidate in the CS department of the University of Southern California. He's advised by Salman Avestimer, Professor Madi Sultan Nolko Tabi, Professor Murali Anavaram, and Professor Tong Zhang. He's also worked closely with researchers and engineers at Google, Facebook, Amazon, and Tencent. And prior to actually joining the CS department, he was an R&D team manager and staff software engineer at Tencent from 2014 to 2018, a team leader and senior software engineer at Baidu, and a software engineer at Huawei. And his research focuses on distributed federated machine learning algorithms, system, and application. So today he's going to talk to us about distributed ML system for large-scale models, dynamic distributed training, and scalable federated learning. So before I turning it to Chaoyang, just one couple things. If you're in the audience and you're a panelist, we'll take breaks during the talk for you to ask questions. So either put them in the chat or raise your hand. If you're an attendee, please use the Q&A feature on Zoom. And without further ado, I'll give it to, Chaoyang.
Okay, so let me share my screen. Can you see my screen? Okay, let's get started. So hello everyone, thank you for having me here. My name is Chaoyang He. I'm from CS department, but work with Professor Simon Westmacher and Madi Sotono Kotabi. So today my talk will it's about distributed ML system for large-scale models. Nowadays people also call it foundation models. I will cover two topics. One is distributed training, mainly happens in cloud clusters. Another one is scalable federated learning, mainly happens at edge devices like your smartphone or some edge servers. So as you may know, these two learning paradigms, although they are distributed computing, but they have different challenges. As you can see in the distributed training setting, normally we need to handle very large scale models. As you can see here, many industry researchers already scale the model to even trillion level parameters, especially in transformer models. You can see it already 1.6 trillion level parameters in the switch transformer. But in federated learning, it's a different scenario that you can see the data, a lot of the data distributed across millions of devices. It's not like the GPU number in cloud cluster environment. So in this setting, maybe the key challenges will be the device may have low computational capability, and also significantly you can see it's very high latency environment. So the communication normally becomes the bottleneck. We summarize this a lot of the challenges in federated learning, like the open problems paper. So here, I think the goal, I want to highlight the goal of these two settings. So in the first, in the GPU cluster environment, normally our goal is to mainly to accelerate the training to make it as a reasonable time. For example, your training may last a week. You want to reduce the training time into a few hours. And in the federated learning setting, maybe the goal will be data and model privacy issue. For example, you're concerned about data set, which may be or includes a lot of customers' information. And sometimes you may not concern about privacy, but you also, it's very hard to migrate the data set into your data center environment. So the difficult data centralization will also be the goal in federated learning. And also you can imagine in the future, like 5G or IoT age, you can see maybe you want to run machine learning at everywhere, no matter it's at your smartphone, IoT devices, or server. So in federated learning, the challenge will be data heterogeneity, and the second one be system heterogeneity. And these two are quite different from distributed training because in the GPU environment, normally you have all the GPU at the same hardware configuration. So there's no such system heterogeneity problem there. And also the trustworthy is quite unique in federated learning. You can see in such a environment, you cannot attack the system, but in federated learning, maybe people are trying to attack the data set and the model to downgrade the training performance. So the goals are quite different, although they are both distributed computing. So in this paper, I want to highlight in this talk, I would like to highlight 3 methodologies that are very useful to do research in these 2 highly related domains. So the first one, I would like to say, normally you can think about dynamic system because the training normally involves a very dynamic system environment, and also how to integrate the stochastic property of machine learning into this dynamic system. This will need to very complicated intersection between multiple objectives. The second goal will be, in my talk, I will introduce a trade-off among multiple objectives, including, you can imagine that model developer normally concerned about accuracy, but in such complex system, accuracy, you want to achieve a high accuracy, maybe the training time is super long, or you may cost too much money to handle the system. So we also concerned about efficiency and security and privacy. Of course, like the federated learning setting, we need to do such trade-off. The third methodology in my mind will be I call it on demand. It means that normally in some, especially in some machine learning applications, we need to think about how to amplify one objective, but do not break the assumption of other objectives. So it's on demand means we want to tailor for one specific requirement in that application. So next, I will use these 3 papers to showcase how we think about in these 3 methodologies. The first paper will be is called PipeTransformer, published in ICML this year. The second one about trade-off is published in Europe's 2020. We call it group knowledge transfer. The last one is the best paper award in federated learning workshop last year at Europe's. So I want to showcase you these 3 papers for details. So first, let's dive deeper into distributed training. In dynamic distributed training, I'm thinking about how to automate elastic pipelining. So this is a paper collaborated with PyTorch distributed team, and we also do some federated learning exploration with them. So let's first look at background. As I just mentioned, the parameter size already scale up to trillion level. And I think we can imagine that this year, maybe people may scale up the parameter size to even 100 trillion. Sorry. So recently, a paper published by Stanford, they call this direction as foundation models. So foundation models means we can train large-scale models like transformer, but it can scale up to any kinds of applications, as you can see here: healthcare, education, large language processing, computer vision. Any kinds of application can reuse this pre-trained model. So, but train such model may cost too much energy, as you can see here. It may cost hundreds of years to finish the training if you run in a single GPU. And you may need to retrain multiple times to fine-tune your downstream task, or sometimes you have to retrain 100 times to turn the hyperparameters. And if even worse is that in some cases you cannot, the model is too big to know the single GPU devices because of memory constraint. So to handle this problem, this key challenge, normally in practice, people may try or reduce based SGD, meaning that in this basic example is that you can see normally we have for example, the 3 GPUs, each one calculate gradient 1, 2, 3. And after the calculation, they can do or reduce synchronization to merge the gradient. So by this way, we can distribute the computation into multiple devices to accelerate the training. But this is just a simple example. As transformer begins to dominate all machine learning applications, people began to think about 2 directions to enhance the training system. The first one is system-wide optimization. As you can see, people already propose many interesting systems from the data and model parallelism perspective. If we think about the data parallelism, we can partition the mini batch. So, and also we can consider interaction between different batches. So in the first case, we call it inter-batch. In another one, we call it inter-batch. And in model-wise, we can also do some partition for the neural network layers. So when you partition the layers, we call it interoperator. And when we vertically partition the layer, we call it interoperator. For example, you can partition the layer into multiple pieces, then it's called interoperator. So in each intersection of these 4 methodologies, you can always find some interesting paper that they try to accelerate training by using these 2 methodologies. So for example, the pipeline parallelism is a way that we have data parallelism, and simultaneously we have model parallelism, meaning that we partition the layer into multiple pieces, the entire neural network into multiple pieces. For example, here we have a model that we partition into 4 sub-functions, like function 0 to 3, which represents, let's say, just 4 layers. And then we can do forward propagation. Each one locates at 1 GPU. But here, the propagation needs to go across GPU devices. So for example, from 0 to 1, we need to pass the gradient, pass the activation map among GPUs. And then once we have the loss function, get the loss from any kinds of loss function, we can do back propagation. And this time we do not pass through activation, we pass through the hidden activations, the gradient. So by this way, we can overlap the communication and computation. So the goal in pipeline parallelism is to reduce the bubble size. As you can see in the live case, if you directly do forward propagation, the bubble size will be very big, meaning that some devices are idle, but some devices are very busy. So we want to shrink the bubble size, and then we can design micro batches to just cut the layers, the batch size into some micro batches. But this way, the batch size is reduced, and then you can see some at some time a lot of GPUs are overlapped together. So that's a reason we can accelerate the training. On the right side, it's a hybrid of data and pipeline parallelism. As you can see, at the end of the forward propagation, what we can do is to run or reduce, meaning that we can synchronize the gradient at the end of the back propagation. And finally, we can update gradient, update the weight by using the latest gradient already synchronized from all pipeline duplicates. So in this case, we have 2 pipelines, and they stand at two machines. So the data rank will be 0 and 1. And in another case is about interlayer, as I just mentioned, we can further partition the layers into multiple pieces, and we can also make this layer in parallel, and simultaneously we have a pipeline for it. So this kind of idea, people call it interlayer model parallelism. A very famous work called Flex Flow try to address this problem by doing an optimal interlayer partition. And another line of work is called, I call it Machinewise Optimization. Because we want to when you want to accelerate the training, besides the system design, you can also think from the Machinewise. For example, you can design efficient model architecture, or you can design efficient training algorithms that make it converge faster. So here there are 4 methodologies. One is to design architecture. For example, people try to make the transformer more sparse. By this way, you can reduce a lot of computation. And then the second line of work is about AutoML. You can search the architecture and make it efficient. And third one is about pooling. Although you have a very complex model, but you can delete some connection by pooling. So that's also a way to accelerate the training. And today I would like to highlight the 4th one. It's called about progress training. I will introduce it for details later. So motivated by these two lines of work, I want to, in this paper, I would like to propose an idea which is called elastic distributed training system. This is motivated by two facts here. The first one is that, as I just mentioned, in distributed training system, people normally consider just about the different layer partition and data partition, but they never see how to optimize the model architecture, how to do SGD optimization. So they just view this kind of machine learning optimization as black box. So this is their, I think their drawback, the major drawback from the system-wise research. And another drawback is from the machine-wise research, they only consider the mathematical form and foundational formulations, how to accelerate the model architecture by redesigning the model. But the drawback is that they never think about how to reuse the system developed by system researchers, like the fancy distributed training system. So my idea is to amplify the two advantages in these two lines of work to come up with the elastic training system. So to achieve this, first I'm thinking about how to do progress training. I think it's a very ideal scenario to demonstrate this methodology. So progress training meaning that we can change the model architecture or the optimizer during the training. I think you are very familiar with the optimizer-wise dynamics when you are doing training. For example, you can change the learning rate during training. So people nowadays call it learning rate scheduler. But in model architecture-wise, I think maybe most of people have not heard about this concept. So progress training means that during the training, we can change the model architecture, but still keep the accuracy. So this is a high-level idea. One paper is published in ICML. It's called progressively stacking. So in this paper, they are trying to double the layer number during training. As you can see here, every time, for example, after step for epoch, you can change the number of layers from 2 to 4. So by this way, you can finally make the convergence faster and also use less resource, because when the layer number is small, you don't need a larger scale GPU cluster to handle it. So this is a basic concept of progress training. Another one is called freeze training, meaning that during training, we can think about from the opposite direction. You can see on the right side, we just scale up the number of layers, but in the left side, we are trying to downgrade the number of layers. So freeze training means, for example, in the first beginning, you have 12 layers, for example, the BERT-based model. But during training, you can reduce the number of active layers from 12 to maybe turn 8, 6. So this we call it freeze training. So both of these two are in the opposite direction to make the network, neural network dynamic. So I'm thinking about how to make it work in the system distributed training system. So here are the 3 key observations. The first one is that we can see very clearly that the computation becomes very unbalanced in pipeline parallelism. For example, if you want to train GPT-3 using the progress training techniques, it becomes a very interesting phenomenon is that when you do, for example, progress stacking or shrink the model's active layers using the freeze training, it will become very unbalanced because some layers are idle and some layers we have to do forward and back propagation. So this is the first problem when applied to pipeline parallelism. Second one will be the memory will reduce very gradually because when you freeze some layers, meaning that we don't need to do back propagation, we just need to do forward propagation for it. In that case, normally we can reduce around 6 times memories because when you need to do back propagation, you need to cache the gradient and also the optimizer states. For example, you want to use Adam, then the optimizer states will be 2 times larger than your model size. So it's a very large memory cost reduced. And the third one would be communication cost. Since we don't need to actively train some layers, then we don't need to do synchronization because we just fix that layers. So we can also reduce some communication cost. So inspired by these 3 observations, we construct such a system, which called is I call it PipeTransformer. It has two meanings. One meaning that the system can transform, meaning that the system can adjust its resource and change the form. Another meaning is that we target for transformer models, especially the giant model like BERT, Vision Transformer, GPT-3. So the idea is that we first run the freeze training algorithm, we design the algorithm, make it on the fly. And the second idea is that we can shrink the pipeline size because the memory is reduced, as I just mentioned. So as the first beginning, we have two pipelines here. As you can see, each pipeline contains 8 GPUs. We partition, for example, the BERT model into 8 partitions, and each GPU hold 1 partition. And then we can do forward backpropagation across so many GPUs. And another server has the same pipeline. So they're connected by DP, meaning data parallelism. So now what we can do is to shrink the pipeline length. As you can see, the first block is white, and then we shrink it to 8 to just 4 GPUs. And this operation, I call it inactive pipelining. And after we have this, as you can see, some 4 GPUs become available. They are totally released by previous pipelines. So they're idle. Now what we can do is to create more pipelines using these idle GPUs. So this step is called AutoDP. It's not that easy. I will introduce later that, as you can see, when we ask new pipes to join the data parallelism, normally what we need to do is to make the data parallelism dynamic membership style, meaning that we have to add some GPUs into these pipelines and add pipelines into the DP, and then connect this new pipe with data parallelism collection. So it's a dynamic membership. So and finally, you have auto cache, which can cache the forward propagations activation map without needing to recompute it, because some layers are become frozen. Then we don't need to recompute the forward propagation multiple times. So we call it this auto cache. So with the help of these 4 components, what we can do is to largely accelerate the training and reduce the energy cost in the training system. So here is a dynamic animation to have you to understand it much better. So at the beginning, we have 2 pipelines stand in 2 servers. Each server has 8 GPUs, and then we shrink the pipe as the layers are frozen, and shrink from 8 to 4, and then we add 2 new pipes like the blue colors, and we connect them within DP, data parallelism, and we can further shrink the pipes, make each pipes to only hold the pipe using just 2 GPUs, and we can further add 4 pipes like the green color shows here. So finally, the entire training becomes a pro data parallelism, meaning that each GPU only can hold the entire model because most of the layers are frozen. So now let's play it again. So we shrink the pipes, we add more pipes, we shrink, add more pipes, shrink, add more pipes, and finally become a pro distributed training on just the data parallelism. So to achieve this, it's a very complex system design. I think today I don't have enough time to cover the details of the implementation, but here I want to highlight this design here. So the design is based on PyTouch API. So during the development of this idea, there's no such pipelining, and we are collaborating with Facebook to develop this pipeline APIs to implement this idea. And we can also reuse existing DDP, data parallelism APIs provided by PyTouch. And also we need to use LACO. LACO is a communication protocol provided by NVIDIA. It can largely accelerate the GPU communication. For example, you can use or reduce, and it make much faster by using GPU direct communication. We also need to use some advanced feature from Python language because here we want to do multi-processing. We want to handle different processes and operate them dynamically. So here, first we have a freeze training component. We can ask this component to decide how many layer to freeze during training. It will check some information from the training. For example, it can check the progress and get some gradient to calculate how many layers should be frozen. And then it will notify the information to output pipe. Then the output pipe will notify will try to operate the pipelines to reduce the number of GPUs for this pipe. For example, here you can see this pipe already is reduced from 8 to 4 GPUs. And it will also notify to AutoDP because AutoDP needs to handle to add new pipes here. So it's a dynamic membership. So you can see here it will reduce the redistribute the data set into 2 parts and simultaneously add a new pipe for it. And finally, we have, of course, we have auto cache to try to cache the forward propagation to further accelerate it. So here's this dissect about the performance. As you can see, the system is totally dynamic, meaning that throughput, the samples per second the system can take is a dynamic curve. It's not a straight line as the normal system shows. So you can see as the time goes, the throughput begins to increase. So finally, it can accelerate training around 2 or 3 times, depends on the model size or what's your communication bandwidth you have in the system. So this is the overall system design and the benefit we have in the system. And you already released this as a blog in PyTouch official website. You can further find some details there. So I also open source these slides. You can check it in my website, and there I will show you how to use some PyTouch API. For example, the pipe, you can just create a pipe by using this API. Just wrap your model and set the chunk number. For example, chunk number is 8, meaning that you have 8 GPUs in your system. But our paper is trying to make the system dynamic, so there are more details about how to do model compression and how to construct the multi-pipe algorithm, and also including the dynamic membership I just mentioned. So I think this kind of API is also very interesting, that it can help us to make the membership dynamic. As I just mentioned, you want to add some new pipes into data parallelism. So normally you can use a new group to create some new groups to handle the active training data parallel workers. So there are some experiment or additional experiment with that. I think you can check here. And the additional highlight is that about auto cache. As you can see in this figure, that we normally we don't need to launch the cache at the first beginning, because at the first beginning, if you cache it, but the forward propagation part may be even faster than you directly load the cache from CPU host memory or even from the disk. So at the first beginning, you can see if we use auto cache, the performance will be lower than we do not use cache. But later, the cache become more efficient because, as you can see, most of the parts you have to do forward propagation. The forward propagation, the time for it is much longer than you do then you directly load the cache from host memory. So this is beneficial of our system. And some feature work like, actually this kind of idea can be applied to many domains. As you can see here, we can make the elastic in cloud-based distributed training system, and also accelerate AutoML by in some extreme large search space, and also in cross-silo federated learning. Here is an example about the use case of PipeTransformer in federated learning. For example, if you have a cross-silo federated learning system, each client has multiple GPUs, you can directly run PipeTransformer in this cluster. For example, you want to train your BERT or vision transformer, but using the distributed data set by using the idea of federated learning. So we can run PipeTransformer here and further aggregate the gradient by using a federated parameter server to do weight aggregation. So I think these are some interesting extensions that make transformer work in more scenarios. So by this paper, I already demonstrate how to design a dynamic system to tailor for stochastic property of machine learning, which will lead to complicated interaction between multiple objectives like the accuracy and training time, and also, as you can see, the memory cost and even communication cost. So I've stopped here for a while to take some questions. So any question about the PipeTransformer research?
None in the chat or Q&A. If you have a question, your panelists, please raise your hand too.
Okay, so let's continue. The second part is about scalable federated learning. So in scalable federated learning, I would like to introduce my recent research in neurons, which can train a giant model on some Earth devices. So currently, you can see PipeTransformer handle the distributed training in such setting that we have micro GPUs in cloud cluster. But what if you want to train a giant model in federated learning setting? Okay, so first let's look at the background of federated learning, which is quite, as you can see here, that first it has some static challenging, and the second one would be it's like we want to do some trustworthy ML here, especially to protect the privacy for your data set and model, and also maybe in the system, we want to make it robust to adversary attacks. And the third challenge will be how we can design some efficient system to make the to reduce the communication and computational cost. And the third one will be so the research we can also think about how to support more applications like computer vision, like language processing, and even data mining, graph learning, for example, the graph learning, and some attack anomaly detection in IoT setting. So here I summarize 3 lines of research that we can try in federated learning. So the first one would be fundamental algorithms. As you can see, how we can handle the data heterology problem, and also like some problems that in the Earth server we may not have enough labels. The second one would be some research about system-wise bottlenecks, how we can improve it. For example, the resource constraint, we want to train a giant model in some smartphone devices, and also how to scale a larger number of users, not just one 1,000 GPUs like the cluster environment. We want to scale up to 1 million users. How we can do it. And the last one will be trustworthy, as I just mentioned. So here is the ecosystem that we developed in the past 2 years for federated learning. So we aim to cover all levels of research in federated learning, including the application, the algorithms. For example, the algorithm I will introduce later. And also we consider the applications like CV large language processing, and the graph learning, and even in IoT setting. And the third one is like the FedML library development and PipeTransformer kinds of research for cross-signal federated learning. So the final one would be, we also try to run some vision and reviews for this direction. So we hope more researchers can involve this direction and solve different level problems. So let's dive deeper into this paper. It's called FatGKT. So I aim to train a giant model at the Earth devices. So in this paper, we demonstrate the concept in convolution in CNN models. So here is then the issue of current training of CNN models. As you can see, even we use AutoML, like the neural net search, we can get a similar performance using around 4 million parameters. This is still big for Earth devices to train. So what if the Earth device does not have enough memory to train such a model? And since this is very key problems in federated learning, if we cannot solve it, we cannot scale up to, and it will use a lot of interesting models developed by CVPI, ICR, a lot of other conferences. So in this paper, I want to demonstrate the idea how to efficiently and effectively train large CNN models, for example, ResNet on your smartphone devices. So first, let's give you a concept about federated learning. As you can see here, that at the first beginning, the server will synchronize the model to a client, and then the client can do a few epochs of training locally. So here, the training is just the local STD. It's not like the or-reduced training I just mentioned in PipeTransformer. So in PipeTransformer research, normally we need to synchronize the gradients for every mini-batch data set. But here we can do training locally for many epochs. So this is a key difference for federated learning. The reason we need to do this is that we want to reduce the times of communication. So if you can imagine that if every time you pass through and backpropagation mini-batch you synchronize with the server, the time cost is too high, right? So local STD is normally the idea to trade off between communication cost and computational cost. And then the client side can further synchronize the updated way to the server side, and the server side will try to aggregate. So the aggregation step here, you can see we just calculated by using the number of data points, which is equal to the number of iterations to join each client and then do aggregation. So here we call it the weighted averaging. So this is called most live algorithm, we call it fed averaging. So actually, researchers also trying to make this aggregation more efficient and more tailored for line ID dataset. So the aggregation equation has a lot of room to improve, to solve some challenges here. And after we have the updated gradient and the weight, we can synchronize the T+1 way to the client side. So this is the entire process of one round of federated training. So federated training will last such a round of training for many, many times until convergence. So from the left side, I summarize this process as the algorithm. So I highlight the three key differences from the previous PipeTransformer research. As you can see here, first, the dataset will be quite heterogeneous, meaning that each client may have different dataset. For example, you want to run a cross-signal federated learning for healthcare domain, you want to run some medical image. Maybe each hospital may have different resolution for that image or different labels. So the data heterogeneity will be the first challenge to run the federated averaging algorithm. The second one will be client training will be a bottleneck if the model size is very big. So here is the question: what if the W is super big? It's beyond the limit of the memory in this device. How we can change? So this is the second challenge. Normally we call it the system-wide challenge, how to improve the system efficiency. The third one will be security. As you can see, when we return the W to the server side, maybe some people, malicious user, will try to hack that model and to downgrade your performance. And even we can hack that model to get the raw data because the gradient contains a lot of information. So these are three lines of work. In this paper, I will try to target the second one. What if the model size is very big? It's like a DM model. So, so to handle this problem, there are very preliminary work that's published in Europe's 2019. It's called speed learning. So this is mainly focused on hospital setting. You can see speed learning. The idea is that we can partition the model into two portions and put the larger portion of the server side. And then we can transmit the intermediate representation like the activation map from the hospital to the server side. So by this way, the key benefit that you can see, each hospital only need to handle a fraction of the model. We don't need to train 100 layers in each hospital. And the server side need to handle most of part of the architecture. It's possible because the server side can normally, we can handle the training by using a GPU cluster. For example, the PipeTransformer kinds of research just accelerate training by or reduce space STD. And then we can synchronize the gradient. By this way, it can also reduce the communication cost because the activation map is normally very smaller, much smaller than the then you directly communicate the weight, the very large model from client to the server side. But the issue is that speed learning has a very weak drawback. I think it's a very serious drawback is that it has to transmit the activation map batch by batch, meaning that it has to synchronize gradient very frequently. You can imagine that in some cross devices settings, especially like the smartphone settings, if you every time you synchronize the gradient from client side to the server side, the issue is that maybe some smartphones are not online, maybe the communication latency is very high, or sometimes the network is disconnected. So structural problem become very serious in this case. So this is a drawback of speed learning. As we can see, as I just mentioned, the drawback of federated averaging is that we have to synchronize the entire model to the server side. So the issue here is that how we can combine the, but the one benefit of federated is that it can do local CD and practically transmit the weight from client to server side. So they both have one advantage and disadvantage. So my idea is that how we can achieve the two advantages in these two learning framework. One is the practical update, meaning that we can do local CD, and simultaneously we only need to train a small portion of the network on each devices. So to summarize, the goal here is that we hope it can be computationally efficient, and it's also communication efficient because we only need to transmit activation map rather than the entire model. And also it can be very low frequent communication because we can do local CD to reduce the communication frequency from client to server. And finally, of course, we cannot downgrade the accuracy. So in order to achieve this goal, I propose a concept named knowledge transfer. So as you can see, in centralized training, we need to transfer data from client to server, a central server and trained. And in federated learning, we have to transfer model and just keep the data set on each devices. So the concept of knowledge transfer will be a little bit different here, that we do not transmit the entire model from client to server side. What we do is to think about this high-level goal. I think this goal, we may have a lot of methodologies to handle this goal, but in this paper, I only demonstrate the concept with a specific example here. So the high-level goal here is that how we can transmit knowledge from many small neural network to a larger model. And finally, the larger model's performance is very big, very good, and it can beneficial a lot of applications. So in the future, hopefully, we can have such a learning paradigm that, for example, the smartphone IoT devices, we have thousands and millions of number of users. We want to transfer their knowledge in very compact neural networks and then achieve a very big model to get a very good performance. So this is the high-level goal. In order to achieve this, here I designed a framework called FatGKT. It means group knowledge transfer. So idea is that we can build the idea based on the speed learning idea, the basic framework. But difference is that we add a classifier to make it train locally. So previous in speed learning, we cannot directly train because we have to pass through the activation map from client to server side. So by adding this optimized classifier, we can train locally, and then at the server side, we can transmit the activation map from the yellow color is the activation map and transmit to the server side. And the server side has another model, which is I call it the server model. The server model has a lot of layers. For example, on the client side, we may only have 3 or 5 layers, but on the server side, we have hundreds of layers. And then once the server gets the transmitted yellow color is the activation map, it can construct a loss function and using this yellow color input, and then it can optimize the server side. So by this way, I additionally add a loss distillation loss here, so it can transfer knowledge from the client side to the server side. And the server will further transfer back the knowledge to the client side, still use the loss distillation. And the training lasts, so it's a bidirectional training from client side optimization to server side optimization, and then ultimately to make the model converge to a state point to achieve good accuracy. And after training, of course, we need to integrate these two model and client model and server model to get a good performance. So this is the formulation. In formulation, is that our goal is to find a good and a small feature extractor on the client side. So feature extractor meaning that the F function, the feature extractor here can be very high accurate to represent the raw data set. So the server side can directly use these high accurate features to train the classifier on the server side. And the server side's goal is to find a great and large classifier by leverage the user side features get by feature extractors. So these are two formulations. And so we have two objectives to optimize. So in order to boost the performance, we use a long distillation, which is a concept used very frequently in model compression. And in model compression, the long distillation means that we can transfer logic from teacher model to student model that, for example, we just add the logic from one neural network, which is from the observed max function, and then transfer logic by using the care divergence loss and just add this loss term to the previous optimization objectives. So finally, we can construct this alternative minimization, which is a bidirectional optimization from client to server, server to client. So alternative minimization here means on the client side, we want to optimize the feature structure, and on the server side, we want to optimize the classifier. So the training will happen like first we train locally on the client side and to optimize this equation, and then we transmit to the server side and to further optimize the server classifier. So this is a high-level idea from the optimization perspective. In order to make it work, we further explore some scheduler, for example, the learning rate scheduler here. So learning rate scheduler here, we use a very interesting scheduler that we schedule it by cross-round learning rate. So normally in centralized training, we just change the learning rate every epoch or in between some iterations. But here we change the learning rate after one round of federated learning, as I just introduced at the first beginning. So another optimization will be local SGD with momentum. We find that if we use live SGD, maybe it does not work well in this case. So local SGD with momentum is the optimal optimizer in our case. And I also try some other optimizer like Adam. They are not work better than local SGD with momentum in our setting. So in the system-wide design, we just cut the model, use the ResNet example. We cut the tiny model into the client side, like smartphone, and then train a giant classifier on the GPU server side. So in order to achieve this, let me summarize the complexity in the system-wide design. As you can see here, the communication protocol will be different because we have to transmit logic. It's not just a model from client to server. So this is different from the previous federated averaging algorithm. And we also need to train automatically, meaning that we have trained client side on the server side. So these are two features that the current training system does not support. In order to achieve this goal, we developed federated FedML.ai. It won the best paper award in last year's Federation workshop. And in FedML library, we can easily support FatGKT like algorithm. So first we have a communication protocol, like it's a communication manager can support different kind of applications, different kind of communication protocol like MPI and MQTT, which is used for IoT setting. And we can also use PyTouch in our framework. In the future, we hope we can support some mobile training with a totally new deep learning framework. So in the algorithm wise, we can easily use these APIs to transmit any kind of research, any kind of data formulation, like the logic, soft labels, and the hidden activations I just mentioned in FatGKT. So the key design is what we call work-oriented programming. So in our reduced space program, we just program in the work, but here we just from the perspective of a single worker, like a single federated client. So by this design, we can directly customize any kind of information for any kind of message definition. For example, we can design message A, B, C, D, any kind of payload for this message or protocol. And also we can customize the topology and define additional message in the system. So this becomes very flexible when you want to do automatic minimization, like I just mentioned, train locally and server automatically. So by this way, we can send message to the server and ask the server when the training is finished and then communicate to the server side. So this is very flexible to design any kind of federated learning algorithm. And in FedML, we also support some customization. So our researcher and users can customize the model trainer. This is very important for different applications. Every time, as you can see that in NLP and CV, maybe the loss function will be quite different. For example, in question answering, the loss function will be different. You want to do image classification. So we give the flexibility to our users to customize the loss function and some training loop. So by this way, FatGKT can is built based on FedML framework, and we can see the training accuracy will be achieved very similar to federated. So accuracy does not downgrade too much, and sometimes even the accuracy can be very comparable and even sometimes slightly higher than federated. And also the computational cost will reduce around 10 times. I think this is very important for if you want to scale a giant model to the client side. And we also think this direction. So let's summarize the benefit of FatGKT. So it's memory and computationally efficient. It can communicate like a local SD and to reduce the communication frequency. And also it can reduce the communication bandwidth requirement because we don't need to synchronize a very giant model from client to server. Just synchronize the activation map will be enough. And also the server side is published data free, meaning that we don't need to additional data set to boost the performance there. And also naturally to support asynchronous training because the server side can directly take the input from any client and continuously train on the server side. So these are the 5 benefits. And we have also think about some extension work, like how to make this activation map screw. So currently this is an open problem. And you can think that when we synchronize the model, we can also, some paper talking about, we can reverse the model's way to get some raw data. So the privacy will be leaked to these malicious users. But also in this activation map, there is also such a possibility that we can get some raw information from this feature map, right? So currently there's no, in academia, there's no such a research that compare them, do a comparison to see whether activation map is more safe than, is safer than the transmit weight. But as I introduced here, there are so many benefits. So I think to make this activation map privacy preserving is very interesting direction because we can achieve so many benefits here. So I think this is it's worth us to try some research here. And in our lab, we are trying to solve it by screw aggregation, meaning that we can add some noise to the activation map, and finally we do not, the server side cannot see a specific client's gradient, and also activation maps. And another direction would be extend from CNN to transform models. And so this is a very straightforward idea. And finally, I want to highlight that FatGKT does not require a homologous model architecture in each client. As you can see in our previous slides, each client can design homologous architecture because we do not transmit the model architecture. What we transmit is the activation and the logic. As long as we can keep these two parts the same, we can design any model architecture in between these two. So for example, here we can use ResNet in some client, and we can also use MobileNet in another client. So this is a very important benefit that I never highlight in our paper writing, but it's a very promising direction we can try. So the long-term goal is to follow this pattern, and we do not transmit data, we do not transmit model, we want to transfer knowledge and to make federated learning more scalable in practice, especially training giant model. So this is my second part. Any question?
Yeah, and I'm also going to give you a 4-minute warning, and there is a couple of questions. The first one, I don't know, Jose Luis, do you want to ask it? I think it's just got answered.
Okay.
The question is, what are the privacy guarantees of the split FL scheme? Wouldn't the intermediate activation leak information about the data at the sites?
Let me see. You mean this part? Yeah, so as I just introduced, yes, in our newest paper, since we mainly construct a learning framework to demonstrate the benefit in machine learning and system-wise, but in security part, actually, reviewer also asked a similar question that how we can guarantee the security for this activation map. So currently, as I just mentioned, it's an open problem. There's no such paper and compare them to say that this one, we can have more privacy than we transmit the model. So this is also our future direction. We want to answer it maybe in our future research.
And the second question in the Q&A is, in progressive training, a portion of the NN is frozen. Can you discuss how you decide which part of the neural network to be frozen and what criteria you have to have other neural net layers to be flexible in learning?
Okay, thank you for the question. So actually I have a slide to introduce it. Maybe here I answer it briefly. So as you can see here, in previous freeze training research, there's no such algorithm that can decide how many layers to freeze on the fly. So in the previous newest paper, they only answer a question how we can compare the similarity between two layers. For example, if you get the activation map of that layers in, for example, T2, and you compare the state in T3. So here the T2, T3 means in different epochs of training. And then we can get a similar score for it. So here we use a different methodology to decide when to freeze the layers. So first we calculate the gradient norm, meaning that we want to check whether the gradient norm change very dramatically. And we find the minimum one that do not change during the training for a while. And then we can pick that layer as a criterion to decide whether we freeze from there. But this may not be an ideal case because some layer before that layer may even change very dramatically. So what we are doing is to use geometric sequence algorithm here. We want to use this algorithm to bound this layer. Maybe sometimes you even freeze more layers. So this bound will narrow down the number of layers to a curve. So the curve looks like this. For example, if you turn the alpha parameter to a very small value, for example, this purple color, though the freeze pattern will be just very slowly freeze. And then the acceleration will be smaller than you use a larger alpha parameter. So it's like trade-off how much time you want to be accelerated or how many layers you want to freeze during training, because more layers are frozen, maybe the accuracy will downgrade a little bit. We tried all these hyperparameters. We find there's a figure in our paper to show the accuracy comparison. You can see everyone is acceptable, but if you're using larger alpha parameters like this one, you may downgrade accuracy more than a smaller alpha parameter, but the acceleration ratio will become smaller from two times acceleration to just maybe 4 times acceleration. So it's a trade-off between speed and accuracy. We can turn it by using these alpha parameters. I'm not sure if this answers your question.
I don't know if.
So finally, can I use just maybe 2 or 3 minutes to introduce the last part?
We're out of time. I'm trying to get I want to be respectful of everyone's time. So can you make it 2 minutes?
Yeah, okay. Just yeah, I can finish very soon. So next part is about on-demand. Actually, I think I already introduced FedML framework, but here I want to highlight in the application level. So in FedML framework, we already have the core framework as I just introduced, but we further extend it into many applications like NLP, graph learning, CV, IoT, and mobile IoT devices. So in FedNLP, we support not just the text classification or lex word prediction like the which is frequently used in federated learning community. We also support script span extraction and sequence to sequence. For example, you want to run the Echo device, like the Amazon Echo device, we can run such kind of model in FedNLP. And for healthcare setting, we can run some object detection and image segmentation model. And in Fed graph learning, our goal is to do drug discovery, which is and also recommendation system, because in some cases we cannot centralize so many graph data sets. So I think Fed GraphNN is also useful. And finally, we want to target the IoT setting. We have a funding about 5G and wireless communication in some router. We want to deploy some, for example, some federated learning client on there and detect some attacks in the network. So every setting, what I mean on demand means that in every setting, every model, the design, the objectives are totally different. So we have to tailor and amplify one property, achieve a very strong feature to support a specific scenario. So this is called on demand. So we have to solve the case by case. So it's very hard to find a universal solution for all these scenarios. So this is the last part. So finally, I want to say just 3 lines of research. Hopefully you can try it by using our PipeTransformer or FedML. And you can, and we also build, our professor also built a trustworthy AI, as you already know it in USC. So currently most of the research is about distributed and federated learning to support so many applications. And so here's the summary, and you can find the paper and source code of this talk and in these 3 links. And also the slide of today's talk is totally open source. You can find my website. So thank you. If you have any question, you can, let's talk offline. Thank you.
Thank you for a great talk. And we'll see all of you next week.
Okay, thank you. Bye-bye.
Bye.